So now we're going to talk about a critically important concept in chemistry that allows us to make a connection between the microscale world of individual molecules and atoms, or small collections of molecules and atoms, and bridge it to the real world of our everyday experience, right? Large numbers of these molecules and atoms. So for example, if we look at a single molecule, right, of water, it consists of two hydrogen atoms and an oxygen atom. And so the mass of our molecule in atomic mass units, right, would be 1 for each hydrogen and 16 for the oxygen, for roughly 18 atomic mass units. Now, if we looked at 18 grams of water, right, different unit, and we were to count out the number of water molecules that's present in this water, we would generate what we call a mole of water, which is a fantastically large set of water molecules. Exactly how many water molecules do we have in that set that we call 1 mole? 6.022 times 10 to the 23rd molecules of water are present in 18 grams. So this allows us to make our connection here. The mole is a number concept, not a mass concept. It's just a fantastically large group or set of things. Now this number is so large, it's very difficult for us to comprehend just how big this number is. So let's give some examples based on everyday objects. So if we were to count out 1 mole of pennies, or 6.022 times 10 to the 23rd pennies, we would have enough pennies to cover the Earth's surface to a depth of 900 feet. And if we were to pick a little larger object like soda cans, if we had a mole of soda cans, it would be enough to cover the Earth's surface to a depth of 200 miles. And if we had a mole of cups of water, it would be equal to all the water in the Pacific Ocean. So when we're counting things in chemistry, the things that we're counting are so fantastically small that we can hold a mole of things in the palm of our hand. All right? So a mole of copper atoms easily fits within our hand. So where does this huge number come from? Well, it comes from our definition that we looked at in Chapter 2. That is, if we ask the question, exactly how many carbon-12 isotope atoms are present in exactly 12 grams of carbon, we can calculate that if we know the mass of a single carbon-12 atom, right, which we measure in a mass spectrometer. So here it is in grams. Again, if we take exactly 12 grams of carbon-12 and we divide by the mass of a single carbon atom, we will get out this number, right, which is Avogadro's number. So that's where it comes from. Now we use this number to count not only the number of atoms in 12 grams of carbon-12, we use it to count everything in chemistry, right? It's just a number. We can use it to count atoms, molecules, ions, whatever we need to count in chemistry. This is what we use. And it's also called Avogadro's number, and we usually truncate it to just 4 significant figures for ease of use. Now, on the next slide, we're going to talk about the mass in 1 mole of things. So if we count out 1 mole of things, we can also weigh out how much that weighs, right? So that's called the molar mass, and it's often a point of confusion for students because they begin to think that the mole somehow deals with mass, but it doesn't. It's a completely separate thing. When you're talking about a mole of something, you're just counting out the numbers of things. That's it. It is not a mass concept. So, for example, when we're talking about a dozen eggs, we think 1 dozen, and we simultaneously think 12 eggs. So in chemistry, when we think about a mole of, say, copper atoms, we simultaneously think about 6.022 times 10 to the 23rd copper atoms. and we haven't said a thing about mass yet. So remembering that the mole is just a number of things, we can ask the question, how much does 1 mole of something weigh? That is called the molar mass. So for example, we can ask the question, what is the mass associated with the number 1 mole of carbon atoms? Well, we know the average mass of a carbon atom. We can look it up in the periodic table. It's 12.012 atomic mass units, right? It's a mass weighted average over all the isotopes. Now, if we ask the question here, what is the mass of 1 mole of these carbon atoms? We'll get 12.012 grams, right? These numbers are linked together by the way we defined 1 mole, right? So we can use this as a conversion factor. When we want to count things in chemistry, we do so by weighing. So we could go out and weigh, say, 12.012 grams of carbon, and having done that, we would know how many carbon atoms we have, right? We could also weigh out something else, like 24 grams of carbon, then we would know we'd have 2 moles of carbon atoms. And the actual number, right, would be 1.2 times 10 to the 24th carbon atoms. So we can use this conversion factor to go back and forth between the masses of things in chemistry and the actual numbers of things. And so this is the molar mass. You'll see 2 different representations for this, right? Here's one ratio. Tell 12.012 grams of carbon per mole of carbon atoms. And you'll also see it in this representation. They both mean the same thing. Let's look at another problem. If you calculate out the formula mass for calcium chloride, you'll get 110.98 atomic mass units, right? That's the weight for 1 formula unit. And then if you calculate the molar mass of calcium chloride, well, it'll be the same number, but now that will be grams associated with 1 mole of them. Well, so let's go ahead and finish up our description here of the mole and the molar mass by looking at 3 different substances, a gas, a liquid, and a solid, each of which have the same number of repeating units. So for example, oxygen and water are molecular substances. They're given by the formula O2 and H2O. If we count out the same numbers of molecules, right, 1 mole of them, we find that they occupy quite different volumes, right? All the oxygen gas will fit in this balloon, and actually at room temperature and room pressure, that same amount of oxygen would fit in about 5.5 1-gallon milk jug containers. Whereas the water, the same number of water molecules fits in 18 milliliters, right, or 0.018 liters. And our table salt here, right, 1 mole of sodium chloride formula units easily fits within this dish. So they have different volumes, right? Gases have much lower densities than liquids and solids do, and we can also see that the mass associated with 1 mole of these are all quite different. So 1 mole of oxygen molecules consists of 2 moles of oxygen atoms total, so the molar mass of O2 is 32 grams. 1 mole of water consists of 2 moles of hydrogen atoms, 1 mole of oxygen atoms, and you add those together, you get a molar mass of 18 grams, and for sodium chloride, the molar mass is 58.45 grams.